Hey everyone. I think it was the first day of class we were talking about linear systems, and I wrote down as a fact that for any linear system there's three possibilities. One solution, no solutions, or infinitely many solutions. You can't have this in-between situation where you have five solutions. So if the system is consistent, one solutions or infinitely many solutions, there's no in-between. We're now in a position where we can prove this. So I'm going to write this down as a theorem for a linear system. And I want to write this in matrix notation, AX equals B. There are three possibilities. Exactly one solution. No solutions. Or infinitely many solutions. One of those occurs, exactly one of those occurs. Right? You can't have multiple options. Now, I want to actually prove this. And so the proof, right, we can verify this now, the proof goes like this. So we've got our system. If it has exactly one solution, great. If it has no solutions, great. Right? What we want to then say is, okay, what if we had two solutions? So let's let x1 and x2 be distinct solutions. What we want to do is show that if there are two distinct solutions, then there's actually infinitely many solutions. Now, I'm going to choose any real number R and let this vector y equal, let's be x1, x1 plus r times x2 minus x1. All right, so we've got our solutions, and in each of those solutions we're viewing as vectors, column vectors, and now we want to define this new vector right here, y. So then let's look at A times y. Okay, well, A times y is going to be x1 plus r x2 minus x1. And then I'm going to multiply this out. So remember, we've got some properties of matrices that allow us to simplify this. This is equal to A x1 plus r A x2 minus r A x1. Now, what do we know about A times x1? Well, x1 is a solution to our original system, which means that A times x1 is equal to B. So this is equal to B. Then we have r times A x2. x2 is a solution, so A times x2 is equal to B. Same thing, x1 is a solution, so here we're going to get r times B. These cancel out, and so what we're left with is B. So what did we show? We showed that AY is equal to B. In other words, this vector y that we concocted is a solution to the system also. So we started off with two solutions. We created this third solution, this new one, but actually we said choose any real number. Well, there's an infinite number of real numbers. There are infinitely many real numbers, which means that for every choice of r, we can create a new solution y. Because there are infinitely many solutions, there are infinitely many such y's we can create, which means that there are infinitely many solutions to our linear system. When we conclude the proof of some theorem, I'll put a little box right here to indicate that we've ended the proof. So now, suppose I want to take a matrix, so let's write it, I need it to be n by n, so suppose A is an invertible n by n matrix. Then for any column vector, let's call it B, and I need this column vector to be of the right size here, so I need it to be n by 1. The system AX equals B has a solution, so has the solution. Now, who would the solution be? Well, to find the solution, multiply both sides of this equation right here by A inverse. If I multiply on the left by A inverse, I will get the identity times x. Well, that's just x. And so what we'll get is x equals, we saw this last time, right? X equals A inverse times B. Now, if y is also a solution, then what we get so then we have AX equals B, which equals A times Y. Now, if I multiply both sides by A inverse, so I have, in fact, let's write this out. So this tells me that AX equals AY. Now, if I multiply both sides of this equation by A inverse, what we get is X equals Y. So we conclude that X equals Y. And so what does that tell us? So you can say thus. Linear systems corresponding to invertible coefficient matrices. So thus, linear systems with invertible coefficient matrices have unique solutions, right? So we said, okay, if we've got an invertible matrix, first notice, no matter who we choose here, if we put any column vector B here, we get a solution. Who is the solution? It's right there. We get a solution, and this shows that there's at least one. This computation right here tells us that there's exactly one solution. Now remember, we had this theorem, we called it the equivalence theorem. And last time what we had, and I indicated that this theorem is going to keep growing, so we had 4 parts. And now, with the computation that I just did, we're going to add 2 more parts. Right? So I should have written E and F. So part E, let me say this correctly, AX equals B is consistent every n by 1 vector b. That's what I showed in the computation that we just erased, right? For every b, there is a solution, x equals a inverse times b. And then part F, the next part of the computation the part that I just erased, told us that not only is it consistent, but it has a unique solution. And so let's say it like this: ax equals b has exactly one solution for each n by 1 vector b. Right, so now our equivalence theorem has grown to 6 parts. And I wish I would have said this last time. What I would recommend, you don't have to do this. I mean, if you're reading along in your book, you'll see as the parts increase. But my advice would be to take a page of your notes, label the equivalence theorem, write down each of the parts, and leave space below. Don't write anything below it, so that as we add more and more pieces to this equivalence theorem, you'll have room for that, and you can add so that by the time we get to the end, right, later on in this class, I think it goes up to about part P or part Q or something like that. There's a whole bunch of parts to this theorem, and we will add more as we go along. Save a page in your notes so that you can add to the theorem as we do. Okay, I want to talk about some special types of matrices now. So we're going to start here with the definition. And n by n matrix A is, now there will be 4 different parts here. The first part, an n by n matrix is diagonal if all entries not on the main diagonal are 0. I'll do examples of all of these once I get the definition down. So an n by n matrix A is upper triangular if all entries below the main diagonal are 0. So in this case, so if you think about the first one, everything that's not on the main diagonal has to be 0 for diagonal matrices. For upper triangular, everything below the main diagonal are 0. So that means you'll have all these non-zero entries up on and above the main diagonal. There's also lower triangular. And so an n by n matrix is lower triangular if all entries above the main diagonal are 0. And then the last piece, an n by n matrix A is symmetric if A transpose is equal to A. So let's look at some examples now. Diagonal matrix, so examples of diagonal matrices. Here's a 2 by 2 diagonal matrix, 1, 0, 0, 2. The main diagonal is the one that runs from the upper left down to the bottom right-hand corner. Right, so as long as you have only non-zero entries along the diagonal, everything else being 0, it's diagonal. So here's another example. Here's a 3 by 3. How about minus 2, 0, 0, 0, 3, 0, 0, 0, 7. Right? Non-zero entries on the diagonal, everybody else is zero. Upper triangular. So upper, and I like to abbreviate it by just putting a little triangle there. So an example of upper triangular. So now I need to draw a matrix where the entries below the main diagonal are zero. So here, there's a 2 by 2 upper triangular matrix. Let's do a 3 by 3. How about 1, 2, 3, 0, 4, 5, 0, 0, 6. There's an upper triangular matrix. I'll let you concoct your own example of a lower triangular matrix, right? Just sort of flip these pictures right here to create lower triangular. And then we also need an example of a symmetric matrix. So let's see, it's symmetric if it's equal to its own transpose. So how about something like this? 1, minus 1, minus 1, 2. There's an example of a 2 by 2 symmetric matrix. If you take the transpose, remember transpose is when you interchange the roles of row and column. And I like to think of the transpose as just taking this matrix and flipping it about that diagonal axis. Right? If you flip it about the diagonal axis, the minus ones just interchange. Another example of a symmetric matrix. 1, 0, 1. 0, 2, 1. Now let's see, I will need a 1 here, a 1 here, and it doesn't matter what I put here. All right, so here's an example of a symmetric matrix. If you take the transpose, right, of this matrix right here, you'll get the same matrix back. Now, diagonal matrices especially, they're nice to work with. So let me write that down. So diagonal matrices are nice to work with. And we will see this as a theme later on. Diagonal matrices are nice for various reasons. So here's one reason that we like diagonal matrices. So what I want to do, I'm going to write down this diagonal matrix here: 4, 0, 0, 0, minus 2, 0, and 0, 0, 1. All right, so there's a diagonal matrix. And I'd like to multiply 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, let's see what happens when we do this matrix multiplication right here. Let's see. Okay, so I'm going to take this row and dot it with each column, and notice what we're going to get is 4, 8, 12. Okay, now I'm going to take the second row, dot it with each column. That will give me a minus 8, minus 10, minus 12. Then I'm going to take the third row, dot it with each of the columns, and what we'll get is 7, 8, 9. So what just happened here? Multiplying by this matrix right here had the effect of multiplying the first column, the first row by 4. It had the effect of multiplying the second row by -2. It had the effect of multiplying the third row by 1. So this is sort of an amazing fact. When you multiply on the left by a diagonal matrix, what happens? The first diagonal entry multiplies the first row. The second diagonal entry multiplies the second row. Third diagonal entry multiplies the third row, and so on if these were bigger matrices. Let's see what happens if we reverse that. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Now what I'd like to do is multiply on the right by a diagonal matrix. So let's see, I need to take the first row and dot it with each of the columns. So what will I get? I'll get a 4, and then I'll get a -4, and then I'll get a 3. Then I will get a 16, and a -10, and a 6. And then I will get a 28, and then I'll get a -16, and then I'll get a 9. So what happened this time? Well, let's see. It looks to me like the first column has been multiplied by 4. The second column has been multiplied by -2. The third column by 1. And this is true in general. When you multiply on the right-hand side by a diagonal matrix, the effect is to multiply each of the columns by the corresponding diagonal entry. So multiplying on the left multiplies rows, multiplying on the right multiplies columns. So that's a nice property. Also, so here's another nice thing about diagonal matrices. So suppose that A is the diagonal matrix and I just want to write this out sort of in general, sort of a generic one. So A1, A2, dot, 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 down to AN. So the diagonal entries are AN, and I have zeros everywhere else in my matrix. It turns out then that if you multiply A times itself, K times A to the K is equal to little a1 raised to the k, little a2 raised to the k, dot, 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 little an raised to the k, and zeros everywhere else. So if you have a diagonal matrix, it's very easy to multiply it by itself. All you do is raise each of the diagonal entries to the corresponding power. So also, if each ai is not equal to 0, then the inverse of A is 1 over A1, 1 over A2, dot, 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 1 over A sub n. So it's the diagonal matrix whose diagonal entries are the reciprocals of the original entries on A. And it turns out, so if any of these entries is equal to 0, then A inverse is not invertible. I want to just collect some properties of triangular matrices. First property, and you can check each one of these. I'm not going to go through the proof, but if A and B are upper triangular, then AB is upper triangular. Same thing, product of, so if A and B are lower triangular, then when you multiply, it stays lower triangular. So AB is lower triangular. And then the last of the properties if A is triangular, so either upper or lower triangular, then A is invertible if and only if all diagonal entries are non-zero. We'll be able to prove this later on, but for now we'll just accept that this is true. So triangular matrices, it's easy to check to see whether they're invertible or not. Right? Just check their diagonal entries. We haven't mentioned symmetric or done much with symmetric ones also yet, so let's also do this. So properties of symmetric matrices. So let's go like this. So let's let A and B be n by n symmetric matrices. The first property, this should be obvious. If A is symmetric, what does that mean? It means that A is equal to A transpose. So if A is symmetric, then so is A transpose. So A transpose is symmetric. So no surprises there. Part B, A plus B, is symmetric. So the sum, the sum of symmetric matrices is symmetric. Maybe that's a little less obvious, but it's not too hard to show. Also, the product of the scalar multiplication R times A is symmetric. And what else? Oh, yeah, last property here. So if A is invertible, then A inverse is symmetric. All right, so the inverse of an invertible symmetric matrix is symmetric. Now, I'm just going to write down a matrix here. So I guess we can say this is an example. No, in fact, I just want to say consider. So consider the following matrix. This is going to be a 2 by 2. A, not 2 by 2, sorry, 2 by 3. So A is the matrix 3, 1, 0. 2, 0, minus 1. And what I'd like to look at is, well, let's first look at A times A transpose. So let's see, that's going to be 3, 1, 0, 2, 0, minus 1 times 3, 2, 1, 0, 0, minus 1. All right, so here's A transpose. And I want to multiply this out, and let's see what happens. So let's see, I'm going to get 10 and 6 there. Then I'm going to get 6 and I'm going to get 4, 5. Okay, so A times A transpose is this matrix right here, 10, 6, 6, 5. Let's also look at A transpose times A. So that would look like this. So A transpose times A is going to be 3, 2, 1, 0, 0, minus 1. And then we'll multiply that by 3, 1, 0, 2, 0, minus 1. And so let's multiply this one out. This will give me a 9 plus 4 is 13. Then I'll get a 3. Then I'll get a minus 2. There's the first row. Then I'm going to get a 3, 1, 0. Then I'm going to get a minus 2, 0, and 1. Now, what are you supposed to notice here? A times A transpose is symmetric, and so is A transpose times A. Now, was that just some sort of amazing thing? Well, was this a coincidence or not? Well, let's look at it in general. If we do, so let's say in general, if I do A transpose, there's some matrix, and I take the transpose of that. Remember how this works. Right? This was back a little while ago. It was one of the properties of transposes. A times A transpose is equal to A transpose transpose times A transpose. Remember, when you take the transpose of a product, here's the property that I'm using. A times B transpose is B transpose times A transpose. Right? So that's the property I'm using here. Now, what's the transpose of the transpose? It's A. So what did we show? The transpose of A times A transpose is that matrix itself. In other words, A times A transpose is symmetric. Similarly, if I do A transpose times A and take the transpose of that result, that's equal to A transpose times A transpose transpose, which is A transpose A. So once again, we see that this matrix A transpose times A is symmetric also. So let's write that down. We just proved the theorem here. So we just proved if I don't even need to say it that way. Oh, yeah, okay. So if A is any n by n, no, any matrix, m by n, I guess I should say, any m by n matrix, then A times A transpose and A transpose A are symmetric. It's really not obvious. I mean, if you just write this down, that's not obvious that this is symmetric and this is, but once you do the computation, it actually works out very easy. So it's actually easy to show. All right, that's a good place to stop. See you next time.